Something monumental is taking shape, hidden deep beneath the American heartland. A secret of cosmic proportions, buried a mile underground. Every day, workers descend into the deepest former gold mine in the United States. But they've traded their pickaxes for particle detectors. They are not hunting for precious metals. They are on a quest for something infinitely more valuable. Something so elusive it's been called a ghost. To find it, they are carving out a subterranean world unlike any other. A network of caverns so vast they defy belief. Once complete, these colossal voids will be home to the largest, most technologically advanced physics experiment ever built on American soil. Imagine a laboratory colder than the eternal darkness on the far side of the moon, containing not one, but 4 artificial lakes filled with 70,000 tons of shimmering, liquid argon. This underground cathedral of science is just one end of a colossal machine that stretches nearly 1,300 kilometers across the country. A machine designed to ask the single most profound question humanity has ever conceived. So, what is this behemoth, and what is it searching for? Before we descend into the heart of this incredible project, let me ask you something. It sounds simple, but it's a question that has haunted philosophers and physicists for centuries. Look around you, at the sky, the ground, your own hands. Why is there all of this instead of nothing? Why does the universe burst with the light of 100 billion galaxies, with stars, planets, and life itself, instead of being an empty, silent void? This isn't just a philosophical daydream. It's one of the greatest unsolved mysteries in all of science. And we might just be on the verge of an answer, all thanks to an experiment called DUNE. The Deep Underground Neutrino Experiment. We are about to dive into one of the biggest scientific quests in human history, exploring the very fabric of our reality. If you find these kinds of mind-bending explorations as fascinating as I do, this is the perfect moment to join our community. Hit that subscribe button and ring the bell so you don't miss our journeys into the biggest ideas shaping our world. Now, let's unravel this mystery together. To understand what DUNE is looking for, we first need a quick lesson on the birth of our universe. In the first moments after the Big Bang, the cosmos was a searingly hot soup of pure energy. As this energy cooled, it began to crystallize into 2 fundamental substances: matter and antimatter. Matter is the stuff you know and love. It's everything you can see, touch, and feel. It's the atoms that make up you, me, and the stars. Antimatter is its perfect mirror image twin. It has the same mass, but the opposite charge. Think of it like a photographic negative to matter's positive print. Now, here's the crucial part. Whenever a particle of matter touches its antimatter counterpart, they don't just collide, they annihilate. They vanish in a flash of pure energy, a perfect conversion of mass back into light. According to every law of physics we hold dear, the Big Bang should have created precisely equal amounts of both. A perfect symmetry. But if that had happened, our universe would be a very different place. Every single particle of matter would have found its antimatter twin, and they all would have cancelled each other out. The result? A universe filled with a staggering amount of energy and radiation, but completely empty of, well, everything. No galaxies, no planets, no life. An eternal, empty glow. But that's not what happened. The evidence is all around us. For some reason, the universe played favorites. For every 3 billion particles of antimatter that were created, the universe cooked up 3,000,001,001 particles of matter. It was this tiny, almost insignificant surplus, this one leftover particle in billions, that survived the Great Annihilation. That solitary survivor, multiplied across the cosmos, became the building block for every single thing that exists today. You, me, the Earth, the Sun. All of us are made from the leftovers of this cosmic imbalance. So, the billion-dollar question that has kept physicists awake at night for decades is, why? Why that extra particle of matter? What broke the perfect symmetry of the universe? For years, scientists have had a prime suspect, a tiny mysterious particle that might hold the key to this cosmic favoritism. They're called neutrinos, but studying neutrinos is a nightmare. They are one of the most abundant particles in the cosmos. Trillions of them are streaming through your body every single second, but they are also the most antisocial. They have almost no mass and no electric charge, meaning they barely interact with anything. They are the ultimate cosmic ghosts, slipping through planets, stars, and entire galaxies as if they were empty space. To give you an idea of just how aloof they are, a single neutrino could travel through a solid block of lead-5 light years, thick before it even has a 50-50 chance of bumping into a single atom. So, if you want to catch one, if you want to even glimpse its shadow, you can't just build a detector. You have to build the most sensitive, most massive, and most audacious trap in human history. This is where the Deep Underground Neutrino Experiment, or DUNE, comes in. It's a project of breathtaking scale, spearheaded by Fermilab, America's premier particle physics laboratory. The experiment begins on a campus just outside of Chicago, Illinois. Here, engineers are constructing PIP-II, the most powerful proton accelerator in the world designed specifically for creating neutrinos. This machine will take protons and accelerate them to nearly the speed of light, then slam them into a graphite target. This colossal impact generates a shower of other particles, which then decay into a pure, focused beam of neutrinos. A precisely engineered hill of Earth then aims this beam downwards, firing it straight through the crust of the planet. The beam first passes through a near detector, located just 600 meters from the source. This initial checkpoint measures the neutrinos right as they begin their journey. But this is just the start. From there, the beam continues its silent, invisible journey at almost the speed of light, traveling for 1,286 kilometers straight through solid rock and mantle, aimed at a second, far more massive target. To understand why, think of a flashlight. If you shine it on a piece of paper right in front of you, the circle of light is small and intense. But if you shine it at a wall across a vast stadium, the light spreads out, becoming much wider and fainter. It's the same principle with a particle beam. By the time the neutrino beam has traveled 1,300 kilometers, it has spread out to be several kilometers wide. So, to have any chance of catching even a handful of these ghostly particles, the far detector can't just be big. It has to be gargantuan. And that brings us to the town of Lead, South Dakota. This town owes its entire existence to the historic Homestake gold mine. For over a century, it was the largest and deepest gold mine in North America, a symbol of the American frontier. When it finally closed in 2002, it seemed its story was over. But a new kind of pioneer had their eyes on this place. Scientists realized that the mine's immense depth provided the perfect shield. A mile of solid rock above filters out the constant rain of other cosmic rays from space, creating a pristine, ultra-quiet environment where only the elusive neutrinos can pass through. It's here, at the 4,850-foot level, nearly a mile straight down, that the far detector is being built. But turning an abandoned, century-old gold mine into a state-of-the-art laboratory was a monumental challenge. The 90-year-old headframe, the iconic steel lattice that hauls everything in and out of the mine, needed a complete, top-to-bottom renovation to meet modern safety codes. The entire steel skeleton lining the 1,500-meter deep shaft was corroded and had to be painstakingly replaced section by section. Then came the logistics. The main shaft is only about 4 by 7 meters wide, and it has to share space with power lines, ventilation systems, and the skips used to haul out excavated rock. The usable space to lower equipment shrinks to the size of a small car. You can't just drive a giant tunnel boring machine down there. Every single piece of heavy equipment, from massive drill jumbos to excavators, had to be completely disassembled on the surface, lowered piece by painstaking piece down the shaft, and then meticulously reassembled a mile underground in the dark. It was like building a ship in a bottle, on a colossal scale. Over several years, crews drilled, blasted, and hauled, removing 800,000 tons of ancient rock to create the 3 main caverns. These are the largest man-made caverns ever excavated, at this depth, anywhere on Earth, each one long enough to lay the Statue of Liberty down 3 times over. To prevent the immense pressure of the overlying rock from collapsing these voids, engineers drilled thousands of holes deep into the surrounding walls and ceilings, inserting and anchoring 6-meter-long steel bolts. This grid of bolts creates a reinforced arch, a cage of steel that holds the very earth at bay. Now, with the excavation complete, these caverns are being transformed. The central cavern will act as a utility hub, while the north and south caverns will house the detectors themselves. This is where the real magic happens. Inside each cavern, a colossal detector module is being assembled. At the heart of each module is a device called a liquid argon time projection chamber. And it all begins with the cryostat, a gigantic stainless steel thermos insulated to keep 70,000 tons of liquid argon at a mind-numbing minus 184 degrees Celsius. The inner walls of this cryostat are lined with a special corrugated, waffle iron-like steel membrane designed to flex and contract in the extreme cold without cracking. Suspended inside this freezing ocean of liquid argon are the detectors, eyes, the anode planes. These are enormous screens, meticulously wrapped with 24 kilometers of hair-thin copper beryllium wire, strung in different directions to form a hypersensitive grid. Each wire must be positioned with sub-millimeter precision. So, how does this incredible machine see the unseeable? While neutrinos themselves are invisible, the traces they leave behind are not. Every so often, one of the trillions of neutrinos, passing through the detector, will, by pure chance, collide directly with the nucleus of an argon atom. Argon is used because its nucleus is relatively large, making it a bigger target for these ghostly particles. When that rare collision happens, the argon nucleus shatters, sending a spray of smaller, electrically charged particles flying off. As these charged particles travel through the liquid argon, they knock electrons off other argon atoms, leaving a trail of free electrons in their wake. A powerful electric field then causes this trail of electrons to drift slowly and uniformly towards the anode planes. As the electrons reach the wire grids, their exact position and time of arrival are recorded. By combining the data from the different layers of wire, computers can reconstruct the particle tracks in breathtaking, three-dimensional detail. While older experiments could see these interactions with a resolution of centimeters, DUNE can see them in millimeters. It's like going from a blurry photograph to a high-definition 3D movie of the universe's most secret interactions. So, what is the grand plan? Once everything is operational, sometime in the next decade, the accelerator at Fermilab will fire its beam. The experiment will alternate, sending a beam of neutrinos for a period, then switching to a beam of their antimatter counterparts, antineutrinos. Both the near and far detectors will meticulously record how many particles arrive and how they behave. The great hope is that they will find a tiny but measurable difference. Perhaps the antineutrinos will interact or oscillate slightly differently over their long journey than the neutrinos do. If they do, it would be the smoking gun, the first direct evidence of a fundamental difference in the behavior of matter and antimatter, the crack in the mirror of the universe. It would be the clue that finally explains the 1 in a billion imbalance that allowed our universe to exist. Of course, science is never certain. The results could show no difference at all, sending physicists back to the drawing board and deepening the mystery even further. But either way, what's happening beneath the plains of South Dakota is nothing short of heroic. It is a testament to human curiosity, a multi-billion-dollar, multi-decade gamble to answer the most fundamental question we can ask. Deep in those ancient hills, there's more than just gold. There's a search for our own origin story, written in the language of ghost particles. They're not just digging for answers, they're digging into the very reason we are here to ask the question,